Welcome everyone. I'm going to, so I planned to talk about very, very recent work, but then I figured out that it's a school after all, so I'm actually going to defer that to the end of the talk. Hopefully I'll get there. And instead of that, spend some time talking about essentially entanglement and things that we can do with states that are Gaussian, like free fermions and bosons. I'll do it, of course, from my point of view. So I'll do a brief review of entanglement scale and its scaling. So these are things that were floating around and mentioned in many of the talks, but I wanted to summarize a little bit what is going on. And then I'm going to talk about entanglement in two types of Gaussian states, for fermions and for bosons a little bit. And finally, hopefully I'll have time, I'll tell you about a new exciting type of quantum phase transition and an exactly solvable spin chain that has this amazing behavior where it can have entanglement entropy that scales actually extensively, like volume rather than sub-extensively. Okay, so let's start with that. So this is the kind of mandatory slide. To define things, we normally talk, you've seen it already several times, we talk about the Hilbert space, and we assume that we can kind of break it into two parts, A and B. So usually we will think about some kind of a tensor product. A generic wave function that you will write on this space will, if you choose any basis of A and any basis in B, it will look like something like this, right? There's some combination. This all possible doubles of vectors span the entire big Hilbert space, which is the tensor space, and these are the coefficients. Now what you do, and that's what Duncan mentioned in his talk, you take these coefficients and you kind of diagonalize them. This is called the singular value decomposition. And this brings you into what is called the Schmidt decomposition of your state. So the new states, psi I and whatever, zeta I in A and in B are, again, these are states that only live in A. These are states that only live in the Hilbert space of B. They are mutually orthogonal, and you just have one index. So this is called the Schmidt decomposition. And it's very, very convenient in order to understand things that have to do with entanglement, because entanglement comes from essentially looking at these coefficients that are responsible for being away from a product state. You can compute the reduced density matrix. This was mentioned many times. In terms of the Schmidt decomposition, that's very easy. It's just diagonal, and the Schmidt if you integrate out B, then you get something diagonal in A, and these are the eigen vectors. These lambda i's, these Schmidt coefficients are, if you square them, they are essentially the probabilities that appear in the reduced density matrix. Maybe more careful definition that works also in cases where you are not sure about how to break your Hilbert space into a tensor product. And this is useful for thinking about fermions and for thinking about field theories, is the following definition, which is morally really the right one, is that a reduced density matrix is something that if you use it to compute an expectation value of some operator that you say live in A, will give you whatever the expectation value of this the operator is in the big space. And this way, you don't need to worry about the actual procedure of partial tracing. It's just a statement about some reduced density matrix in region A that gives you the correct expectation values. Okay, so there are many characterizations of the quantity of quantifying the entropy that sits in this new reduced density matrix A after we got rid of B. Schmidt number, entropy, Renyi entropy, we already heard, all kinds of mutual information. The definition I will mostly use is just the entanglement entropy, which is minus trace rho log rho. von Neumann entropy of this reduced density matrix. These are the trivial examples for every product state. When you do the Schmidt decomposition, you will only have one term, and the entropy is going to be 0 because it will be a pure state in the reduced system. For a singlet state is an example of a maximally entangled state, and the entropy is 1 for a singlet. Yeah, for this, yeah. Yeah, it's a log 2. So yeah, I will freely switch between log 2 and natural log, randomly throughout the talk. So if you have a log 2 that's floating around, if it's multiplicative, it's not a big deal. If it's an additional one, then you know that it has to do with degeneracies. But I don't think I'll put any. So entanglement entropy is a non-local version of correlation functions because it doesn't depend on any particular points we are looking at. And as we all know, it can be non-vanishing at 0 temperatures, and so it's very different from thermodynamic entropy. Here is a quantum information perspective of where you, what this quantity means. Let's say you take we are going to take a wave function defined on HA and HB. And in this case, we're just going to think about HA and HB as Hilbert space of spins. And you can ask the following question to try to quantify for a state how entangled it is. Let's say you had an arbitrary number of copies of your state, and you're only allowed to do local operation and classical communications between the two, between A and B, Alice and Bob. Then you can ask, by doing these operations, how many maximally entangled states, how many of these singlets I can generate in the system. And so the asymptotic number of these maximally entangled spins is given by this entanglement entropy. Okay? Now, it's not clear how to generalize exactly this type of argumentation for many body states, but at least it gives you a feeling for if you have a lot of entanglement, that means you can do some operations on the system and get these singlets that then you can, at least, for example, these people like Bennett would be interested, can you use that to do some quantum operations, quantum information associated operations. So that's one thing that this entanglement entropy quantifies. Now, in our context on condensed matter, what we are going to be interested in is mostly in phases of matter, and to understand how entanglement behaves differently in different phases and what does it quantify. Here's an example of phases of matter. This is, of course, the transverse field Ising model. There's a phase transition when the coupling of, say, sigma x in the Hamiltonian vanishes, then the spins point in the z direction, and there is a doubly degenerate ground state. When g is infinite, then everyone wants to point in the x direction, and in between there is a quantum phase transition. The nature of the dynamics here is quite different from the dynamics either on this side or that side. So here is a brief summary of what we kind of know. So first of all, many of these quantum phase transition points, if we are looking, so we are physicists, we always look from afar on these things, like we do an S wave whenever we are looking at whenever everything is spherical to first approximation. So low energy physics in many of these systems is defined by something called the conformal field theory. And the conformal field theory is characterized by a conformal charge. And this is a universal quantity in the sense that you only care about the low energy properties of the system and not about the particularities of how you got there. And for these types of systems, the entropy scales in a universal way. It goes like the entropy of a region of size of length L goes like log L times the central charge. This is a little bit, usually you would see just central charge divided by 3. And this has been worked out by already Halsey, Larson, and Winchek in '94, and Calabresi and Cardi in 2004 did various improvements and more cases of this. Okay, now more even pertinent from a practical point of view for condensed matter is, of course, that this, and I'm sure Adrian Fagin will talk about it, this entropy tells you how good you can simulate things, in the sense that if entropy scales fast, then there are many non-trivial correlations built in between different blocks of the system, and it will make it hard to simulate. And in particular, procedures like DMRG, density matrix renormalization group, depend on how fast the number of relevant degrees of freedom grows when a system block becomes larger. And the number of relevant degrees of freedom scales like e to the entropy, as usual. And so for gap systems in one dimension, this e to the entropy saturates. And it means that even if you take a very, very large system, it doesn't make the problem much harder than a smaller system, because you don't really add many degrees of freedom for each block. Even if the system is critical in the sense of, like in a conformal field theory, where we saw that S is logarithmical, then exponent of S is an exponent of a log, and it's still a linear thing, or maybe a power law, but it's not exponential. So it's doable, and we use it for various critical systems in one dimension. It's much harder to get anywhere in 2 dimensions, and that's a very active field of research. I should say that that's just to highlight the end of the talk, when I was kind of copying and pasting this from an old talk I gave once upon a time, I noticed that I wrote here, how many quantum critical 1D systems are conformal field theories. Here there appeared the word all. All quantum critical 1D systems are conformal field theories. And that's kind of a common misconception that I got that I had, and because that was my impression for many discussions with people, and many other talks that say that. But as you'll see in the end of the talk, not all critical points are describable by a conformal field theory. So that will be an explicit example in the end. OK, let me continue. What happens in dimensions larger than 1? So in dimensions larger than 1, well, for bosonic fields, we know that there is something we call an area law, the entanglement of a region in space. For simple free bosons is just scales as the boundary area. And that was indeed the first case. This was computed as a correction to black hole entropies. And Matt Hedrick mentioned that. We also heard a little bit about what happens for topological states. So for topological states, the entropy goes like some non-universal leading term, but then there is a subleading term which is constant and has to do with the log of the quantum dimension of the system. And at the time when I first saw that, and I didn't know anything about topological systems, I thought that's a very mysterious and amazing formula. Now I think it's like almost obvious, and there's a very simple intuition, at least that I have, is that if you are looking at a finite region, so in these topological systems, what these quantum dimensions measure are the degeneracy of the states if you put the system on a torus or in a higher genus surface. And what happens is basically, if you're looking at a finite region, for any state in the finite region, you cannot know in which of these ground states you are. And in particular, if you would try to write a Schmidt decomposition for any Schmidt state that you will have outside the region, you have that state. or that state with some kind of a non-trivial loop maybe going through it, a Wilson loop that changes the ground state, right? So there will be always essentially asymptotically these D states, and these states will give you this extra piece, this degeneracy, because each of them will appear exactly in the same way in the Schmidt decomposition. And that also explains why all of the Renyi entropies will also have this independent of the Renyi index. So we heard from Roger, I believe, right, that they don't depend on the Renyi index. And that's exactly the explanation, because he also told you that for a maximally mixed state, Renyi index is the same as, Renyi entropy is the same as regular entropy, right? So that's the reason for that. Yes?
I think this capital D is not the degeneracy of ground state on the torus for
no, for non-abelian, so it's an asymptotic statement. So if you put asymptotically many, it's the case when you have the number of holes in the system goes to infinity. That's what it.
I think capital D is related with the torus.
Capital D is the total quantum dimension.
I see.
Yeah.
But I mean, it's not the degeneracy. The ground state on.
So again, the statement is that if you have, when I say torus, I mean a torus with asymptotically large number of holes in it. Okay? Then the number of the degeneracy grows so the degeneracy grows exponentially with D. Yeah? Sorry, that wasn't clear. Yeah. So the number of holes to the.
It doesn't have to be D.
Sorry.
D can be not an integer.
So sorry, the D to the number of holes. Yeah. Okay. So this is general statements about some systems we know about. And now the problem is that many of those we cannot really compute things exactly, although. And it would be it's nice to have at least some benchmark systems where you can do things and see in all gory details what entanglement entropy is and so on. Okay, so I'm going to talk about several of these models, and there are going to be two types of models, and all of them are systems with quadratic Hamiltonians. First, I'll talk about fermions, and then I'll talk about bosons. So again, throughout this talk, there are many, many references that I didn't put, and so on. This is a partial list of people that collaborated with me on some of these works. Since I don't know what exactly I cited, I'm just putting them all there. Okay, so what's the main thing that we are going to use? The main fact about quadratic Hamiltonians, the reduced density matrices are Gaussian states, and also you can think about the ground state as Gaussian states in the sense, these are non-interacting systems, and therefore all correlations obey type of a weak theorem, right? So anytime you have many operator correlation, you can decompose it. This could be either operator or bosonic, or in this case fermionic. You can decompose it into pairs, product of pairs. That means that to describe the state, if I have my system and I partition it into, say, region A and region B, anything I can compute, the state in A is completely determined by all 2-point correlations inside A, right? Because I can then use Weak's theorem to express any many-body operator sitting in A and compute its expectation value, right? So therefore, correlation functions in A will contain the full information about the state. How do we do it explicitly? So you can actually it's an exercise. You start, let's say, you're familiar with the most simple type of correlation function, which is just the average number of fermions, for example, in a system at temperature 1 over beta. It looks like the Fermi-Dirac factor, 1 over 1 plus e to the beta e. Okay, you can check. It's a trivial exercise that it's true in a general basis. If you look at the correlation function between a two-point function between point I and point j. It's given by, now it's as a matrix, 1 over 1 plus e to the beta h, where h is the single particle Hamiltonian. So, right, the single particle Hamiltonian has eigenvalues e k. Now, the other thing you can do, so I'll call this matrix M, and I'll use it often. What else you can do with it is, for example, you can take this relation and invert it. And given M, you can always find an effective Hamiltonian, right, for which the correlation functions are going to be M. So it's given by that, and this is called an entanglement Hamiltonian. You can even compute it explicitly sometimes. The spectrum of this entanglement Hamiltonian is the entanglement spectrum that Duncan Haldane was talking about. The reduced density matrix then can be written explicitly in this way. Okay? Now, you can look at properties of this matrix. It has eigenvalues. It's positive. The eigenvalues are between 0 and 1. That's just a consequence of looking at this 1 over 1 plus e to the h effective. And if you diagonalize this M, the spectrum of it corresponds to probabilities of occupying various states. So these are effective fermionic modes that are relevant for entanglement. I already wrote this before, but if you write the reduced density matrix in this form, then you can use your basically basic formula for entropy of fermions at finite temperature, and it goes like this. The entropy is just, in terms of the matrix, some trace of m log m plus 1 minus m log 1 minus m. Or in other words, it's sum of the probability for every mode of this, once you diagonalize, of every mode to either be occupied or not occupied, which is the case that will give you the entropy for fermions, for independent fermions. I want to mention that there are other quantities that are given by this matrix M, like the number variance. Okay, so that's just given by trace m times 1 minus m. OK, now let's look at the maybe most important application of these things, and let's think about a Fermi C. Right? So now we have fermions. To define the state of, so we will have some Hamiltonian like this, ek minus e Fermi times the Heidegger A, and the ground state of this Hamiltonian will be to fill up all the k modes such that ek minus e Fermi is negative. And that defines for us some region in momentum space, which we know as the Fermi C. And I'll denote it by gamma. Okay? The Fermi surface is the boundary of gamma. And then we want to ask what happens, what is the entanglement of a region omega in real space? So now we have to look at this formula for the two-point function in real space for this type of problem. Explicitly, it looks like this. So I'm these chi's, I put them to say that chi's are functions that are 0 outside this region omega and 1 inside. So this is just to restrict M to be inside our region. You don't have to worry about them yet. And the other part is just basically the Fourier transform of this region gamma. Right? That's what you will get here. You just write it in momentum space and then go to real space. Now, what's the main feature of this type of a matrix, of an operator? Well, this part, and this just comes from translational invariance, depends only on x minus x prime. So it's some operator that, or some matrix whose elements depend only on the difference of the indices. And then it's multiplied by something that restricts it to some region. We know of these things in one dimension. These are called Topless matrices or Topless operators. These are Topless matrices are matrices where the elements are constant along this kind of diagonals. They only depend on I minus j. Okay? And there's a well-established mathematical theory to deal with these objects. These go by the name of Szego theorems and Hartwig-Fisher asymptotics. And they deal with the question of what if I take only a block of this kind of a Topless matrix, and I want to know some information about its spectrum, or usually about its determinant. Right? So how does it look like when I make the block larger and larger? And there is a way of expressing that in terms of the Fourier transform of the coefficient setting there. Now, here's a formula. So this has been studied a lot, and the Topless matrix. But in higher dimensions, much less, because it's a much harder problem. But it turns out that there is some work on this done by Harold Widom and later other people, which gives you the asymptotics of so let me explain again what's going on. So this is an analog. If I look at higher dimensions, this is an analog of a Topless matrix. So I'm looking at something which is translational invariant, just a function of x minus x prime. And then I look at a block of it, right? And then what I'll do, I ask what's the asymptotics when I take this block to be larger and larger. So will I take the linear dimension of omega to be larger and larger? And so there's an analog formula to this Szego-like formulas, which is due to Harold Widom. And if you use that formula plus plus this expression for the entropy, you finally find the following asymptotics. So this is the entropy of free fermions given a Fermi C, this is this gamma, and given a region and real space. Okay, so you see that the scaling is a little bit fast. It goes like L to the d minus 1 log L. And there is some geometric factor that sits in here. So there are many ways of understanding more intuitively what's going on. You can think about if you have higher dimensions of various ways of cutting the system into one-dimensional strips and their contribution. But this is essentially this is the asymptotics for entanglement entropy of fermions. Now let's continue a little bit with measuring entropy. So we heard from Rajibul about that a little bit, and I'm going to now concentrate on fermions. You can also talk a lot about other situations. And the main clue here is that particle number fluctuations have some things that are in common with entropy. So if you take this region A and you ask how many particles are there, right? Then remember I told you for this type of systems, basically we can think about each as a bunch of independent states that can either be occupied or not occupied by a fermion. And so the entropy has something to do with measuring this probability distribution, but also the number fluctuations. It shares various properties with entropy. But let me now quickly tell you the kind of main conclusion there. So it turns out for these quadratic type theories, for these non-interacting fermions, that you can actually make a relation between entropy and number fluctuations. But it turns out you just the variance of the number is not enough. You need to know the entire distribution of particle fluctuations. And this is measured by something called the full counting statistics. So what you do is you form a function. So Pn is the probability of measuring n fermions inside A. You form this Fourier transform, sum of n Pn e to the I lambda n. This Fourier transform, take the log of it. The Taylor coefficients of the log are known as cumulants. And these are in principle measurable quantities. So the first one is usually called the signal, then the fluctuations are the noise, skewness, and then many, many, many more. Now I'm going to explain that if you know all of these cumulants, or in other words, if you know chi of lambda, then you also know the entropy. And the reason for it is very simple. So for these simple systems, you can have a very simple formula for what this function is. It looks like a determinant of 1 minus m. This is always our old m, plus m times e to the I lambda. And this just represents the fact that if you are in the basis where m is diagonal, this determinant breaks into a product. And so if you remember, dig and remember how you prove things like the central limit theorem and so on, remember the main trick there is that if you look at independent processes and then you take the Fourier transform of them, it becomes the product of the Fourier transforms. So it's exactly the same story here. The Fourier transform of this total number is actually a product of the Fourier transforms of each independent mode here. Now, what's the main thing you want to notice here is that, of course, this is a function of lambda. So it has a lot of information. It's not just one quantity. Entropy is just one quantity. And what you do is you basically, if you know this chi of lambda, then you can, from it, reconstruct the spectrum of m, and then use it in order to compute the entropy. And then you get these kind of amazing formulas like this one, for example. So the entropy, you can express it as sum over cumulants times some combinatorial factors. These are Bernoulli numbers. It's a pretty amazing result. We're very happy to find it. This is a work with Leonid Levitov. And it's not completely right because it's beautiful, but it doesn't converge almost. It will almost never converges. If you want it to converge, you actually have to do a different type of expansion. I'll maybe mention it later. But I want to show you how you can use this in principle to measure entanglement entropy. So here's an example of how you do it in the context of a quantum point contact. So here is, so this is by now an old work. The idea is very simple. I want to measure fluctuations in the number of particles in some kind of Fermi sea. If you look at quantum wires, it's kind of well established that to a good approximation, fermions go there with linear dispersion. And what they do is basically, if I have a quantum point contact, where there are two wires that are disconnected, there'll be fermions coming from this side with linear dispersion. That means they just move without changing the shape. So if you put a kind of a delta function here, it will just move along with a constant Fermi velocity. So what you do is you basically look at a closed point contact, then you open it for some time, and then you close it back. And then what you will have is that some of the fermions that were coming from this side will move there, and some of the fermions that came from this side will move here. And if you now measure, this thing will manifest itself as a noise, because there will be fluctuations, right, in the number of particles that passed, because there were fluctuations in the number of particles in this region. Okay? So you can do that, and then you compute this chi of lambda. And you find that it's a Gaussian, it's given by e to the minus lambda squared times log of the time where you kept this thing open. And now what you do is you just say, OK, this is this C2, right? Because it's essentially the Taylor coefficient of log of chi lambda. You multiply it by this Bernoulli number divided by this factor that I gave before, and what you get is 1 over L3 log t. And this is really nice. Why? Because this is exactly the CFT result, right? It's appropriate for these free fermions, which is C over 3, and C is 1. This is just a slide about how you can resum this series to get it to be convergent, but I'll skip that. OK, so these are some things that you can do with fermions. Here's a quick review of things you can do with bosons. Well, not review, just one example. And I'm going to give a quick crash course of what to do if you have free bosonic systems, non-interacting bosons. So non-interacting bosons, again, what you should imagine is essentially a bunch of harmonic oscillators. So some Hamiltonian that looks like something quadratic in x's and p's. Right? So there'll be x's, and for each x there'll be p, the canonical conjugate. I'll just bunch them together in one big vector. Now you can check that the commutation relations, right, between these elements of the vector are given by some matrix sigma, which is sometimes known as the symplectic matrix. It's written here. It has kind of one upper side. There's 1 on one side and -1 on the lower left side. Now, the same way, right, these systems are Gaussian and they obey Week's theorem. So everything should be given in terms of the matrix of correlations between these x's and p's. You can sum them up together into a correlation matrix, covariance matrix, gamma. And basically, the entropy will depend only on the eigenvalues of this gamma, and in particular, not really the eigenvalues, but what are called symplectic eigenvalues. The reason for that is that you're not allowed to do just any type of orthogonal transformation to mix between these modes, because you have to preserve the commutation relations. So when you diagonalize your set of harmonic oscillators into modes, you need to use symplectic transformations. Symplectic matrices are matrices that preserve this, are transformations S that preserve this sigma. So they preserve all of the commutation relations. And so under a symplectic transformation, you can bring this gamma into a kind of a type of a diagonal form. Okay? And the eigenvalues are the symplectic eigenvalues. Once you did that, then everything basically boils down to the same story. Now A's are not fermions, they are bosons. But again, you can essentially have your entanglement Hamiltonian, and the eigenvalues of these Hamiltonians are given by this combination of symplectic eigenvalues. There is a nice trick, because symplectic eigenvalues are hard to compute. It turns out that if there are no cross correlations between p's and x's, you can actually, instead of that, take the product of the correlation of x's and the correlation matrix of p's. So these are basically two sub-blocks of this big correlation matrix gamma. And if you look at their product, G times H, then lambda squares are the eigenvalues of this one. And that's also an exercise. Once you have that, everything else is very simple. You just go ahead and use your whatever you know about just free harmonic oscillator. And then the modes are independent, and you just sum over them. So one way of writing the entropy is this way. So it's a sum over. Before we had something like lambda log lambda plus 1 minus lambda log 1 minus lambda. Here it's something that's similar but not the same. OK, so I will quickly give you an application of this, which I think is kind of amusing, and at least I enjoyed thinking about it. And that's the following. So I want to compute entanglement of a bosonic field, but instead of just a bosonic field in a region, I'm going to take a different type of entanglement. So you can always ask about different ways of cutting your Hilbert space. And usually, the real space entanglement cuts are kind of natural. There are many others that are kind of arbitrary. Here, my motivation was slightly related to what actually David Hughes was talking about, is to ask, if I have a field in the presence of a dielectric material, and I try to think about it at 0 temperature, does that thermalize the field in the sense that David was talking about? Right? So the whole system is at 0 temperature, but I have interaction between the dielectric and the field. Does it mean my field is in some effective temperature? Right? So the answer, one would guess, is no. But because at least in this setup, and I'll show you explicitly no and what you get. So here is the way you set it up. So I'm going to to use the electrics in Hamiltonian formalism is a little bit awkward because they have information about frequencies and so on. So it's better to think about it in terms of in this context, it's in terms of an action. And what it looks like is, so this is phi is some scalar field. You can think about some component of quantized electromagnetic field. And there is some kinetic term here. And the electric function enters in some form which looks like this. That's to obey kind of whatever the analog of Maxwell equations you would want here. Once you have the action, you can use it to compute all of these correlation functions. So the action is quadratic. And so I can use the tools that I told you about from a moment ago. So for example, you can compute field correlation functions. It's just an integral of inverting this thing because it's Gaussian. And there's some tricky assumptions there, which I'm going to forego. Here's a simple example first, where really nothing interesting happens. So let's say I took this epsilon, and I assume that it's dispersionless. So there's no omega dependence, right? Then I claim that there is no entropy, right? So as soon as the dielectric function is frequency independent, there is no entropy. And the explanation is here. Essentially, if epsilon is frequency independent, then you can get this action from a Hamiltonian, right? So the system doesn't have external memory because of coupling to something. And you can write a Hamiltonian for the system. And since it has a Hamiltonian at 0 temperature, it will have no interesting entropy. It will be in a pure state. So then you want to really put a dielectric function that represents some interchange of energy or something with the medium. By the way, this is an example just to see how this formalism works. If you compute, now I'll take again epsilon, which is a dielectric function, which is just a constant. I can compute these correlation functions, and what you will find is that the correlation functions of the field are exactly kind of the inverse of the correlation function of the momentum. And when you multiply them together, you'll find that this g times h is kind of boring. And when you compute the entropy, it's going to be 0 for all k modes. OK, so now let's put in something more generic. So let's put in a dielectric function that looks like this. Again, you need to do the calculation. And this is roughly what you get for the effective energy as function of k. Everything now is diagonal in k, so I do every k separately. And I want to see if that I can think about it in some way as a thermal state. In thermal state of photons should be something where I have something linear, for example, in k for the energies, right? But that's not what you get, of course. Now, that's not surprising, and we already heard in David's talk. In this system, essentially, every k is conserved. K is conserved, so I have so many degrees of freedom. And there's not enough, I guess, phase space for them to really mix up and give me a thermal state. So this type of a model dielectric function does not, that's the conclusion, does not serve as a thermal bath for the radiation field at 0 temperature. OK. Now I have how many more minutes? I'm going fast, so that's good. OK, so now the rest, I think I have 10 more minutes. I'm going to devote them to.
While you're on bosons,
Yeah.
another thing you can do with bosonic states is squeeze them.
Yes.
Has there been
And
discussion of when you have a many boson system and you squeeze it in a many boson way, where you're squeezing it in some way? That's a way of generating entanglement.
right.
Has that been worked out?
I wouldn't be surprised, but I don't know. And I don't know. And I also I don't know of any other work doing this kind of thing, except for this one. So the main thing
Is this in the end this squeezing also? Each mode gets squeezed?
Yeah, but in a different way.
But what's happening is each k A mode is getting squeezed independently
Right,
by
right.
its own amount.
Right.
Whereas, so, yeah.
Right.
So
That's
the
essentially
question,
what's
if you
happened.
had a many-body
Right.
system and it was squeezed in a
Right.
many-body way, that's a way of generating entanglement.
Right.
Seems like that's
So,
something that.
so there is you can compute there is entanglement, of course. So now the field is entangled with the matter, and you can compute that. I didn't put it in here, but
But it's just one
yeah.
mode.
And the thing I don't understand exactly is this. What's the meaning of these modes, special modes, once I had diagonalized the system? Anyway, so let me now quickly tell you about something which is much newer from the last year. Actually, two of the people that worked on this are here, Amar Ahmadain and Rafael Alexander. And this has to do with the question of how much entanglement I can have in something like a spin chain with a simple local Hamiltonian. So here is a recap of what I already told you with slightly more added to it. So this is our formula for entanglement entropy. And first I should mention maybe the most important thing, which is that for a generic state, the entropy scales like volume. Generic in what sense? In the sense that if I take a big Hilbert space and I take a completely random vector there with no choose it completely as isotropically, then and then I chop my system, then the entropy will scale like volume. The same as thermal entropy. Now, for gapped systems, we believe that there is always an area law. There is no rigorous proof. There is, in one dimension, there is a rigorous proof. In higher dimensions, it's highly likely, but no one managed to prove it so far. So here's a homework for you. There's actually, so Matt Hastings proved it in 2007, but since then there are much improved proofs, exponentially better proofs by Arad et al. For free fermions, I showed you our result, which is there is area times a logarithmic correction. And for conformal field theories, we saw C over 3 log L. So this generic state is a random state. It's not a ground state of any local Hamiltonian. Local Hamiltonians are very, very special. And the examples we know of are all go like area law, maybe with a log correction. So the question is, can you do more than that? So in fact, there is, I was very surprised to learn about this. There is already a model from 2010. It's kind of obscure paper, very, very, I found it impossible to read. But Sandy Irani actually finds a model where the local Hilbert space dimension is 21. And she has an argument why, if you look at some type of random sets, their entropy is going to scale with the volume. So some of them, with some probability. I should mention there are models which are not translational invariant that allow you also higher entropy scaling. Maybe the nicest one of them is by these Spanish groups, where these are just free fermion, not non-interacting fermions like the one we talked about, with a particular Hamiltonian, which is completely local. And so you can compute, at least numerically, everything. And there, the Hamiltonian couples, the coupling in the Hamiltonian decays exponentially away from the center. So it's very nice, but it's not really satisfactory if we want to talk about things like scaling, because that would mean that if I want to make my system larger, I cannot just attach to it copies of itself. I need to attach it with completely different couplings, right? So I cannot really scale properly. There are other models by Mevasa and Shor and also Salberger and Konrapin that don't have this linear scaling of entanglement, but they have square root scaling, but they are translationally invariant, apart from boundary terms, which we always have to put. And so I'm going to show you a new model where we have a really nice phase transition. So the model has a Hamiltonian. It's inspired by this model of Mevasa and Shor. It's a Hamiltonian. It depends on a parameter t. For t less than 1, entropy is bounded. There is an area law. If t equal 1 is just the point of Muvasa and Shor, and entropy scales square root. And as soon as you put this t 1 plus epsilon, the scaling of entropy is linear. Okay? And the nice thing about it is that everything is exactly known. Or at least all of these statements, you can write exactly the ground state and check everything. So here's the kind of type of state we are going to get. I'm calling it a rainbow state. And the idea is the following. If you wanted to create a highly entangled state, one thing you might want to do is you think about generating, say, electron-positron pairs and put them in a strong electric field that will drive electrons one way and positrons to the other direction. And if they are created in a way which is, for example, they could be created entangled in spin, then you'll be creating all of these pairs that are maximally entangled and separating them. So that's the type of state, but I don't really know how to do this as a ground state. So we're going to do something like this, but it's in a slightly different way. I want to, and the way this entangled is this where the word rainbows come from is basically in a concentric way like that. Pairs are entangled. Another one I want to mention, another rainbow state I want to mention, which is cute because it sits actually in a lab at the University of Virginia. Olivier Pfister has a nonlinear cavity where he pumps into it lasers. The laser does a down conversion into pairs. So the sum of energy of the pairs have to be constant, 0 in this reference frame. And so you get a kind of coherent superposition of all of these pairs. So that's a rainbow state that sits actually in a lab. OK, so how can we get that? And before I continue, clearly here, if I cut the system here, the entropy is going to be the number of pairs I cut. So it's going to be like the length, right, of the half the length of all of this thing. Right? It's going to scale linearly. The type of Hamiltonian I'm going to show is frustration-free. So let me tell you what is the definition of a frustration-free Hamiltonian. So we write the Hamiltonian as a sum of terms. And we say that it's frustration-free if these terms all individually annihilate the same state. These things are assumed to be positive, and they all annihilate some state psi. It's the ground state of this Hamiltonian. Frustration-free just means that there's no competition between them. They all agree that this psi is a zero energy state. Okay? And there are many examples of that. Some of them, so any classical Hamiltonian, such as Ising, for example, is a frustration-free system. The toric code is frustration-free. AKLT is a free, so that's the model that Haldane was mentioning is frustration-free and so on. Now, typically, these models are commuting and gapped. So the easiest way of getting something frustration-free is if these HIs are just commuting, yeah, and you can diagonalize them together, and they all will agree on some ground state. Okay? And this is what happens in this case, these two upper cases. But in AKLT model, for example, the HIs are not commuting. Yeah? So it's a little bit tricky to see that it's so that it's frustration-free. The one thing which kind of this suggests is that frustration-free models are gapped. Because certainly these cases are gapped. But this is not true in general. And a nice example of why of this not being true was presented by Sergei Bravi and friends. They write a Hamiltonian for a spin 1 system. I'm not writing the Hamiltonian right now. I'll write it in a moment. And the ground state of the Hamiltonian is a sum, can be thought of as a sum of what are called Motzkin paths. So these are these mountains. And what they do, and I'll explain all of that in a second, what they do is they show that the entanglement entropy of this, if you cut, for example, the system in half, the entanglement entropy grows logarithmically, while we know that if the system would have been gapped, it should be constant, right? That's what Matt Hastings proved. So therefore, the system cannot be gapped, and then it's critical in the sense that the gap closes as we take the system to be larger and larger. The next step is that, and this is what got me interested in this, is Moassa and Shor showed that you can actually, but you see, this is a log entropy. So it's still some kind of thing that's similar to what we expect for CFTs. So you can now argue whether it's a CFT or not, but it's not clear-cut obvious that it's not a CFT. So what they did is they said, OK, let's add the color degree of freedom in a particular way to these walks. And they found that now the entropy goes like square root. So it's much, much more entropy than before. So I'll explain how you can get that. Let me first explain what are these mountains. So in the first case, we're talking about a spin 1 model. So basis state for our model is some spin configuration where each point is either 1, 0, or -1. Okay? And now what I do is I map one. There are two different ways of looking at it. One, I can map it to an up move, 0 to a straight move, and -1 to a down move. So any spin configuration like that will give me some walk. Yeah? And the Motzkin walk is a particular type of walk where I start from 0, I go back to 0 in the end, and I never go below 0 in the middle. Okay? That's a Motzkin walk. Another way of interpreting this, representing these states is in terms of parentheses. It's also kind of nice and will be useful for the next, for adding color. You can think about 1 as opening parentheses, 0 as doing nothing, and -1 as closing parentheses. So what are Motzkin walks? Motzkin walks are really ways of putting parentheses in a sentence in a grammatically correct way, so that I will never have more closing parentheses than I have opened. Right? If I do that, that would be the same as this trajectory going below 0. Right? Now, let's say I have two types of parentheses. Right? Then I can talk about, so say I have two types of parentheses, and now my local Hilbert space has -2, -1, 0, 1, and 2, 5 states. I can write a general spin configuration in this way, and then I can map it into a walk like before, but now I have two colors. I can either go with 1 or go with 2, and I can put them with different colors. Okay? And, or I can use different parentheses. Now, this is the crucial thing to observe. If we add this extra type of parentheses, the rule for these walks is now a little bit enhanced in the sense that still I'm looking at a mountain that goes from 0 to 0 and never cross below 0. But every time I go down, I have to look to my left and see the last time I went up at the same height. And then when I go down, I have to go down exactly with the same color. Okay? This just means that if I open a square bracket and I do various things before I close it, right? So there will be always open, close, open, close, open, close. And in the end, I have to close it with a square bracket. Okay? So that's this kind of a special correlation that builds up in here.
And the thing inside the square bracket is itself chromatic.
Yeah. So this, right. So now the colored Motzkin paths, right, are again the grammatically correct ways of putting more than one type of parentheses. By the way, if you look at the combinatorics literature, there are other definitions of colored paths which are completely different and useless for this purpose. OK, so how do I build a Hamiltonian for this? So here is my ground state, right? How does it look like, or the state I want to get as a ground state? Well, there is a completely flat move where I don't put any parentheses, and then I start putting parentheses, and there are various things. And I want to build a local Hamiltonian that will annihilate this. It will be made of positive terms and will annihilate this. So I want to use some kind of projections. So since it's local, I have to compare between states that appear here that are only different in some small region, right? Because I will work with my operators on this. So for example, I have two mountains here. And they're exactly the same outside this gray area. right? So what do I have in the gray area? So the only rule is that I need to be, so whatever is outside, inside I will have a superposition of either having up straight or straight up, yeah? For any choice of what I put outside. So then I build my Hamiltonian out of projectors on things orthogonal to this up straight and straight up. So if I want to kill up straight, straight up, I project it on, colors are different, but up straight minus straight up. Right? That's the orthogonal thing. So this will automatically kill these kind of things, these kind of combinations. There are three types of projectors like that you have to write down. So up straight minus straight up, and up down minus down straight. Sorry, and up down minus straight straight. So the main rule is just that the height difference going from here to here has to be the same in the two terms. Yeah? You sum over all this, and you also add penalties for having things with unmatched colors, like up with red and down with blue. That will correspond to parentheses that are not matching. And final thing you do is you add boundary terms. So in the end of the spin chain, you add the term that penalizes starting your mountain by going down. Right? This will give a positive energy to using down for the first spin, and penalizes finishing the mountain with going up. And turns out that this is enough. Now let's see how the entropy works out in this. So it's actually pretty simple to understand. So let's look at a trajectory like that. And let's say this is half the spin, half the system size, for example. Right? So this is some random path. Now, these paths are essentially like random walks. So there are random walks with the wall, but otherwise, they're deep in the bulk here. They don't really care that there was a wall. And then you can ask, OK, what is the information that is transmitted from side to side? Okay? And that will give me a clue about the entropy. If my trajectory went to a height m, right, what does the other side know? Well, it will have to start from the same height to go down to 0. And it will have to look back every time to see what was the color of unmatched going. So there are unmatched steps up, m of them, on the left side, which I have to give the same color when I go down on the right side. Okay? So there are m bits of information here that have to be shared between, that essentially are completely mixed between the left and the right state. And now you ask, OK, if it's a random walk, what's the typical height? Well, it scales like the square root of the time you made the walk, so square root of this n. So you have square root n number of bits, and that gives you immediately entropy, which is square root of n, right? So a very nice result. OK, so now motivated by this example that I told you before about sending particles to the left and to the right and putting a field, you can think about this type of a thing, right? This type of a projector is something that creates a particle and antiparticle. And then you want to somehow spread them to go to the left and the right. So you can try we tried many different ways of doing it. The tricky part is that you want to do it in such a way that you'll still have an exactly solvable ground state that you can really nail down the problem. One thing you could try is to put coefficients before these different moves. Turns out that for the system to be frustration free, they need to obey some consistency relations. I'll skip that. And I'll just say that the simplest thing that you could have tried in this way actually works. So what we are going to do is we are going to take these operators, these projectors that we had before, and just put a little t parameter here. Okay. What does that mean? That means that when I project, for example, on the state which has like up, down, plus a straight, straight, the up, down will have to appear with a t. relative to the straight to be annihilated with that, right? And similar thing happens here. So if you count these t's, you find that overall, if you have any kind of a trajectory, it will have a factor of t to the area under the trajectory. So basically, if you want to compare this state with a state where, say, I went straight here, then I will not have one factor in t, and so the area will be smaller. So that's how you get this. Okay? So this is our new type of wave function. And this is now wonderful, because now we have a parameter. We have a Hamiltonian. We know that we can prove that this is the ground state and that it's unique and so on. And we can ask what happens. And now, well, I'm not going to bother you with that. Let me actually just look at this. So, so now what happens? So if t is very small, right, then I prefer to have small mountains, right? So when t goes to 0, really, I'm very close to basically going all the way 0 like that. So that kind of a state will not have entanglement. So I have basically an area law for that kind of a state. So essentially almost a product state. It's a little bit more complicated than that, of course, but that's the moral. For a large t, what do we get? So large t, the major contribution is going to be for the maximally high mountain here, right? So that's going all the way up and all the way down, right? And so if I look just at that case, then I immediately see that this type of a state will have linear scaling of entanglement if I cut the system in half, right? Because each up is not compensated before I go to the right side. Yeah? So the basically triangular mountain will give us this entropy, which scales as volume. I want to mention, should I mention that? There's another model. You can do the same thing with spin half type systems, but there is a price to pay. You have to have three neighbor interactions. So you can do that. The model is a little bit simpler because there are no straight lines. It's only up and down. So some combinatorics is simpler. It's simpler, but the Hamiltonian is slightly, well, not even more complicated, just slightly longer range. In the few minutes that are left, I'll tell you about a few more things about it. Actually, I have more time than I thought. Yeah. So, so first of all, let me emphasize, this is a completely new type of a quantum phase transition. It really doesn't look like anything we had before. So there is a kind of area law type phase for t less than 1. For t larger than 1, it's not that we are in a critical point. We are on a critical line. The whole of this line is gapless because it has to have this huge entropy. And the point itself is special. What do we know about excitation gaps in this system? So for the uncolored case, the entropy, I said, is going like a log. And gap is polynomial in the system size. But for t larger than 1, and with the colored case, then so entropy is linear. S here is the number of colors. And the gap can be bounded from above by t to the minus n squared to the divided by 3. N is the length. Right? So it's a gap that goes so fast to 0, faster than exponential. So I had a simple argument why it's going to be exponential, going exponentially to 0. And I didn't even try to make it good enough to see how good I can make it until Levin Movasa basically told me that, no, it goes like t to the minus n squared. And they use some sophisticated math to get that. But in fact, you can get a better result by just doing variational approach. Let me give you an example of how you can bound the gap. So to get an upper bound on the gap, all you need to do is guess a good wave function that has low energy. Right? That's what you need to do. So which is orthogonal to your ground state. So one simple thing you could do is, for example, if you have a system like this, you can take, for example, the last spin and change its color, right? Then automatically you are orthogonal to your original system because now the sum of, now you have uncompensated left brackets or right brackets. It's going to be completely sitting in a different sector. And now you can ask, well, you know, since these things are so far apart, how long will I have to so to know that I switch this color, I will have to apply the Hamiltonian many, many, many times to even feel that. And so you can make this argument in a kind of more rigorous way and see that if you do this, you get, actually, if you do this explicitly, then you get a gap bound that goes like t to the minus n. If you want to be a little bit more sophisticated, then you can switch the color of the largest interval that appears here before you touch 0, and then you get this t to the minus n squared over 2. So the gap is extremely small. And also for the, you can also do the same thing for the colorless model. OK, so now I have maybe 5 more minutes to describe what are some of the next steps we do with this model. So you already heard a little bit about tensor networks, and you will hear more from Adrian Fagin, I believe. But our next task is to say, can we describe this state in terms of a tensor network? And let me quickly explain. A tensor network is a prescription to compute coefficients in a wave function. So this is the type of variation wave function with a prescription how to compute these coefficients. So sigma 1 to sigma n is some kind of a spin configuration. And you define our wave function. I need to tell you what this is. So you choose, so an example for that is a matrix product state. You choose a bunch of matrices. And this should be 2, 3, whatever. You choose a bunch of matrices for each, depending on if the spin is up, down, or whatever value of the spin is. And you just take the product of these matrices, and that gives you this coefficient. It's just a rule of how to compute coefficients, and that defines for you a variational wave function. You can describe it in illuminating gray in terms of a tensor network. So the tensor network should spit out a number given these. So there are input legs, this sigma 1, sigma 2, and so on. So these are the spin configuration that you want to put in, and it should spit out the amplitude for that state. So you do it by just contracting this tensor network. This describes some tensors. These are free indices, and you just sum over them. Okay? And you get a number. Okay? So this is what is called a matrix product state. It's the simplest type of tensor network. You can immediately see that for any matrix product state, the entanglement is going to be bounded. How to see that? Well, basically, you can evaluate or upper bound the entanglement by seeing if I want to isolate a region of some length, all I need to do is cut out 2 legs. That kind of describes, in a way, how much influence I can get from the environment. And essentially, the number of these legs that you cut tells you an upper bound for the entropy. So for any matrix product state, you only need to cut 2 legs. And therefore, entropy is always bounded. It doesn't matter what the length of the region is. Right. So now, OK. So now, in our case, of course, you can build bigger tensor networks, right? So this is a matrix product state. It cannot clearly cannot support high entanglement, but you can add more and more layers of these things and get higher entanglement. And so that if you want to isolate a region, you have to cut more and more legs. And so in our case, because we know that there is, at least for large T, we know that entanglement is going to grow linearly, it means that really we need to have a linear number of layers going up in order to get such entanglement. But the nice thing about this state, which makes it distinct from most of what people do here, is that because we have a geometric picture of these coefficients, we can actually represent as t to the area, we can represent this computation in terms of a simple tensor network. How will it look like? Oh, sorry. Well, so Raf here that sits somewhere there, I tasked him with doing that, and he came up with some drawing with pipes, stuff like that, which is essentially this. But first they were like pipes and taps or something. Anyway, so we want to encode all of these mountains, and the way to do it is, okay, I mixed. So one way of representing these tensors, it's kind of awkward sometimes to write exactly tensor with all the indices and what it gives for any combination of the indices. Instead of that, you can, if you can, replace it with pictures and say that the rule is that basically the pictures have to match. That's already a tensor network for you. You can then, if you want, write it in terms of indices. So in this case, each of these squares is going to be a picture. One of these type of pictures, I actually should show them here. So there are several types of pictures. And they have colors and arrows. And any state that once you say what are and the boundary has been for some reasons deformed here to sit on this triangle. Once I tell you what are the spins and what are the colors here, then this defines for you essentially a unique type of a non-zero combination of these arrows. Okay? So it will give you a particular coefficient. And it will give you 0 if it's not a non-Motzkin walk. So basically, if you have like this, like we said, maximal type of tree with a particular type of colors, it would look, you will use this type of pictures and glue them together. It looks a little bit like one of these spin models, like ice model and stuff like that, just with its own weird characteristics. And this would translate into that. And you can have more examples. So I want to stress that this is really something which is, I did not put the t's there. So each of these has also a t that you have to multiply. So I want to stress this is exact. So mostly what we hear about when we're talking about matrix product states and the tensor networks, these are variational wave functions. And there are almost no examples, very few examples where we want to think about them as exact ground states for anything which is local. So in fact, any matrix product state is an exact ground state of a local Hamiltonian. These are called parent Hamiltonians, but the Hamiltonian will have a range which is log of the dimension of the bonds that you have to use there. So it will be typically a highly long range of Hamiltonian. The one kind of nice example where we have a short range Hamiltonian that has a matrix product state ground state is actually the AKLT chain, which is Haldane talked about once upon a time. And in fact, it can also be described in terms of some subset of these Motzkin walks. So maybe I'll
this thing, the bonds have some small integer number.
Yeah. So you can see it's just basically the numbers of ways you can connect this with any of its members. So it's basically, 7, I think, something like that. Some small number, yeah. And this is exact. Now,
for this is 2 colors. You put 3 colors there, but you could.
2 colors. You can also put 1 color. Okay. It's still correct. But then you want, and here we come to an interesting point, right? So now you say, okay, this is really nice and it's exact for any t, and you can do it for any number of colors, right? But but there are a lot of tensors here, right? And you would expect that if you have lower entanglement, like for example for t less than 1, you don't really need so many tensors there. It should be something more like a matrix product state, right? So there is some non-trivial way in which this network can be optimized by maybe not into an exact network, but into a matrix product state, which will only have like maybe a layer of these things, which will depend on t. We don't really know how to do it effectively. And I think that's a very interesting question, especially if you go to the t equal 1 point. So the t equal 1 point, for the colorless case, we know that the entropy grows logarithmically. And then we expect that you should be able to describe this state in something more like a Mera, more like a tree-like thing, which has kind of automatically logarithmic entanglement. When the system is with a color, then t equal 1 has entropy that goes like a square root, right? And we don't know, I mean, what's the best way of representing that. I don't think you can do it exactly like here. For exact expression, you probably need the whole square grid, but there must be a way of deforming it. So here's the homework for you. There must be a way of deforming it into something nicer and more efficient. And this is kind of an ongoing project which we're trying to finish. I'll maybe leave you with an example of some things you can do. And the interesting thing about it is that it doesn't, so you can numerically try to generate a Mera, for example, for t equal 1. But you can also try to invent things because the system is simple enough. Here's an example of one thing you can do. Let's say you wanted to describe the state where the sum, so now where the sum of spins is now without a color, right? So spin 1 without a color. And you want that only to retain the condition that the trajectory starts from 0 and goes back to 0 in the end. So I'm allowing my Motzkin walks to go below 0. So they're not really Motzkin walks anymore. So it's more like a Brownian bridge. I go from 0 to 0. And I want to describe that, for example, in terms of tensor network. So here's an example of how you can do that in a tree-like fashion where you add up. You need to basically sum n numbers and see that the sum is equal to 0. Yeah? So you can do it iteratively by summing larger and larger blocks. And then you get a tree-like thing. It's very, very different from Mera. But it still retains some semblance of this type of tree-like behavior. Anyway, so there are many, many things like that that we're thinking about these days, how all of this is related to holographic, to holography. So we call these exact holographic networks because that's what they are. Right? I go into the if I want to know something about the boundary, and so there is a one-to-one correspondence between any spin configuration in the boundary, on the boundary, and a particular configuration in the bulk. So these are an exact holographic network, and you can, of course, debate what does it mean. Can you get a metric associated with? Can you relate it to the holography in the sense that Matt Hedricks was talking about? I have much to tell about that, but I don't have time, so I'll maybe stop here. I don't think I prepared the conclusion slide, but the conclusion is that there's still lots of stuff to do with entanglement. Even the free fermions and the free bosons, there's still many, many unanswered questions there, even though it sounds simple. Once you go down to the mathematical details, it's really, really hard. And of course, we have new types of models and discover new things about quantum phase transitions. So I'll stop here.